much time. Good afternoon. I want to share with you my experience on using the different components available in Eclipse to build the system engineering workbench adapted to your needs. So who am I? I'm Mélanie, and I'm working as software developer at Obeo, mainly focused on system engineering tools. So first, what is the problem addressed by system engineering? The purpose is to build a complex system like planes, trains, or robots. And building a complex system requires multi-activities in multiple domains. Some teams have to define processes, some others have to specify and implement the system, verify the quality, manage the different people, the different teams, and the different stakeholders. And all this from multiple different domains like mechanics, electronics, software, and many others. So the main issue is to manage the system complexity and the organization complexity. How to keep the consistency of the system and not lose important information between all the specification, conception, production, and validation steps. To manage the increasing number of interactions, it is necessary to share the know-how, enhance the communications, and avoid breaks in the process. One solution is to adopt a kind of platform approach, one common referential addressing the different issues. The workbench we will develop in the demonstration it will be used to define the Wally robot. This system would be an independent robot which has the mission to clean the Earth, and it will have some requirements as to use the solar energy, protect itself when encountering a danger, and to be able to communicate with other robots and humans. So as developing a plane, a train, or a robot do not need the same activities, engineers, and tools. As each company has its own process, habits, and knowledge, the workbench used to build the system should be different and adapted to each specific needs. This table illustrates which components we will integrate in the demonstration workbench. We want to manage the requirements, describe the system, specify the software, generate some documents for the quality assessment, provide some specific domain tools, and be able to export and import data for interoperability. Our first need is the ability to define requirements. For this, we will integrate an existing Eclipse component named RMF. The requirement modeling framework is based on the OMG Requi standard and will provide the graphical editors that we will use. So here we can see that we have installed on the Eclipse platform the RMF plugins. And now we are creating a new Requi document. In this document, we first define the structure of the requirement document. So we will define some new specification type. We will define the requirement type with the three fields: the description, the ID, and the honor. There is another type with, which would be the headline with the description. Some other things we define is the ability to create automatically the ID of the requirement. So the requirement ID will be generated automatically when you create a new one. Then we can specify also some representation information like which number of columns is visible. So here we have only 3 columns. Then when we do this, we can create the first headline. The headline will define, in fact, in our system, the different Wally mission. And when this would be done, we could define all the requirements for our system. Then the first requirement would be for Wally to clean the Earth. And there is many others, like explore the world, collect the waste, compact the waste, and many others. OK, then we will need tools to specify the system. As we did for the requirements, we decided to integrate in our workbench existing standards used for system definition. So we integrate XML and UML languages in Eclipse, which are defined in Eclipse. And we decided to reuse an open source tools available on internet for graphical edition. So here we are using the SysML designer. With it, we will specify the different elements composing the Wally system and the functions. So here we are creating a SysML project. Okay, it's a little bit long. In this SysML project, we will create first a block diagram where we could specify a system. Here, the first main system block would be the Wally block. And we will have so many other blocks, like the robot controller with many functions, like compute the route, protect the robot, and the other block, like a social network controller, an energy controller, and many other things. For each block, we can define also an internal block diagram to specify the interconnection of the different system components. Then, with the UML language, we will specify the software embedded in Wally. We create first a package diagram to define the software structure. Then we will define the different classes. Our software is composed of robot controllers that will manage the robot speed, a motion controller to refresh the robot position and send some new commands to the engines, a sensor driver that detects the obstacles to build the map of the world. And hereafter, we use also UML to instantiate the different blocks of the Wally system. Okay, this is a good start point, but it appears soon that existing tools does not cover all our expectations. We need to extend our workbench. First solution would be to use the classical Eclipse extension points to customize the workbench. But if nothing existing fits our needs, another solution is to fork the open source tools. So we decided to fork the existing SysML designer on GitHub to update it in order to be able to integrate the requirements already defined with the Reqif format in our SysML designer. Then the next need is to complete the SysML standard in order to reference the Reqif requirements from SysML block. So we will develop a really simple DSL that will be used to link a SysML block element to a Reqif requirement in order to represent that the block satisfies a requirement. So we create a new IMF project here, and we defined an eCore model. This eCore model will be named the reqif-ext for Reqif extension. In this model, we will create then a main container, which would be the Reqif extension. And then we will have two different kinds of elements, which would be verify and satisfy, which are relations. When this is done, we can see that we add some attributes and references to our relation element. First, we will add an attribute which is the name of the relation, and then two references. The first one is a SysML element that reference a class element from the SysML from the UML model, and the second one was the requirement, which would be a specification hierarchy from the Reqif model. Finally, we just have then to create the gen model in order to generate the code, and we can use the generated code and the generated editor in our workbench. So next step is to integrate the new DSL in the graphical editor. Okay, this is not working. Okay, I missed some videos. I'm sorry. Okay, something is missing. I'm sorry. So, yeah, generated. This one? I think it is, yeah. Come back. Yes. Then then we update the SysML designer we forked on GitHub, and we customize the different graphical designer in order to integrate in the a new viewpoint to attach a requirement specification to a system model. And then we update also the existing editor view in order to update the requirement cross table in order to use the Reqif elements. And then we update the block definition diagram in order to add a new layer to be able to see in the block diagrams the different requirements that satisfy a block. Here, if we come back to our workbench, we will see that we added one viewpoint, and this is the new viewpoint with the new kind of representation. This representation allows to attach to a robot system the new Reqif specification. Then we will see that we can create the requirement cross table. This table allows to see on the left all the requirements defined in Reqif format, and at the top all the blocks defined in the SysML designer. Okay, it is possible to allocate a requirement to a block. And then we will see that we have created a new model file, which is Reqif Ext, where you can find all the satisfy relation. Here we are seeing that in the block diagram there is a new layer requirements, and by activating it, we will see all the requirements that satisfy a block directly. So then, DSL, we can say that DSLs can be also used to complement the models with concept missing in the standards. Here we will develop a new DSL, another one, to specify the ability of WALI to communicate with others and create a textual editor to easily write the WALI's dialogues. So we are using Xtext to define a really simple grammar for the script language. This language will be used to define the dialogues of WALI. So we can see that the dialogue is some sentences. The sentence is made with a description optional, and characters and double dot and some words and sign. Then after this, we will generate the Xtext artifacts in order to provide a textual editor to the user. And when this will be done, it will be available for us it will be easy for us to integrate this textual editor to our workbench. So here we are generating the Xtext artifact. And when this is done, we can relaunch our workbench with the new editor available. Okay, so in this editor, we can see that we have defined two script files. The first one shows that we can have some highlights on the name for the different characters. We can see here that if you don't define some good characters, there is a warning. And we can see that it is really easy to integrate this editor. So if we sum up what we have in our workbench, we have tools relative to the system domain, but we will need other kind of tools specific to other domains, like safety tools, performance tools, code generation, document generation tools. And it is interesting to see how simple it is with EMF models to define links between all these domains, and how tools can provide navigation links from one domain to another. So first classical tool we integrate is a generator to generate C code from the UML system software model. So we use Axeleo and the module already provided on internet on EPL license in order to generate the code. This module is named the UML2C module. Then we just generate some chain to launch easily from our workbench the generation. Here we are creating the launcher. We select the error log, the output folder, and which UML model will be used for the generation. So here we select the UML model we defined earlier in the system designer. And we generate the code. We can see that it is some C and H files are generated for the robot controller, the sensor drivers, and the other things we define in the class diagram. We refined our update speeds function and some other function for the vision control. So The CC and H files are generated according to the UML description, and thanks to the big Eclipse components catalog, it would be easy to integrate to our workbench a code editor adapted to C language by integrating CDT and some static code analysis tool like Codan. Then we develop and integrate another DSL to add timing information on the UML model. First, we want to specify the timing constraint on the UML model, and then get real execution traces by running the application on the target and pull up this timing information to the conception model. The application in the example is an image processing application used by Wally to detect the shape of the different objects existing in its visible environment. This is the vision function that we defined in the UML system, using UML in the system. And this vision function must process 24 images per second. So to express this characteristic in the software, we will have to define two timing constraints. For this, in the sequence diagram, we add a new tool in order to add first one timing constraint on the periodicity and the second on the timing response. Then, after running the application on target, we will get some traces that we inject in the UML model. Here we are just selecting the traces, and we're injecting these traces in the UML model. When this is done, we can refresh the actual view, and we can see directly in the UML model the measured elements. And using some other views like the timeline view, we can go through the execution and see directly the execution in the UML model. When this is done, we have also provided some other views, like a chronogram view, in order to see for each function exactly its execution. Still, with the timeline, you can go through the execution. And there is some other view that generate a kind of report about constraints. Here you can see that some constraints are not valid, and so some constraints are violated, and you can see the expected and the measured value. Then there is some other kind of views like charts. So another link we want to develop is between system and safety domains. It is really important for the safety engineers to link the safety analysis directly to the system definition. Thus, we integrate to the workbench a specific modeler dedicated to safety analysis. This modeler allows us to define a simple risk analysis, and I will show you quickly how to create a preliminary risk analysis. So first, we go to the dashboard to link the safety analysis to the robot system. When this is done, we can create a new risk analysis scenario. So next steps would be to first select the hazard generating the accident. So the hazard would be here an excessive speed of Wally. Then we will have to select the context in which this will occur. The context would be acceleration in an unknown region. And finally, we will have to select the consequences of the accident. Here, the consequences are robot damage. And we have to select also the severity, which would be critical. Okay, as our system and safety tools are both using EMF models, it is possible in the safety analysis to reference directly some system elements. So that's why here we are creating a preventive barrier, which would be associated to the robot controller. And we can associate exactly which function of the robot controller will be in charge of this. It would be the protect robot. Then it is easy to navigate from this safety view to the system view. As you can see, we can navigate directly from the system to the block diagram. And in the block diagram, we can activate a new layer that we added, which is a safety layer. And directly from in the system definition, we can see that a block is a safety block. OK, so then it is also possible to generate some documentation. Because when you are developing a complex system, you will need the ability to export information. For example, for some quality, you will have to generate some quality documents for quality assessment. Here, we are defining, for this purpose, we are using GenDoc2. This is used to generate documentations related to the risk analysis. And we are defining just a simple template that would generate a report for safety analysis. This is using Axelio. We add a new menu to integrate GenDoc2 in our modeler. And we just have to then select the template and the output file name of the new OpenOffice document. If we open this document, we can see that this document is related to the analysis we just defined before. OK. Then, another important thing is to document the different views of the system, and most importantly, to keep the documentation consistent with the system evolutions. That's why it is possible also to be interesting with some other tool like Mylene Intent. And using all these tools, the documentation integrated with other Eclipse would be, with other Eclipse tools, then becomes really, truly useful. Then during all the project development phases, we will have to share data between other Eclipse tools, some proprietary softwares and some free softwares. As all the tools cannot be integrated directly in the platform, it is important to be able to export and import the data. For example, in the demonstration workbench, we can export a timing constraint defined on the UML model to another Eclipse-based tool, which is named Simtas. And this tool will be used then to analyze some scheduling results. OK, so the important thing is for all domains to work on a common referential. This means that we have to share the data. Here again, Eclipse provides some useful existing tools, like CDO, in order to persist models in all kinds of database backends and manage the multi-user access, Git and SVN that are well-known version control tools, and EMF Compares that is a useful tool to find and manage the differences existing between the EMF models. OK, so but before developing a new workbench, you have to pay attention to a number of points, in fact. Do you want to use standards or custom language? It depends. If the semantic must be really precise, DSL is good choice, except if a standard addressing your domain already exists. Else, use standards. If you need to be able to analyze or validate your model, the choice of DSL facilitates the creation of customized tools. But if you have a model for documentation or communication purpose, you will have to use standards as they are already well known by many people. If you think about cost, the standards will be cheaper as you can reuse existing code tools. Otherwise, with DSL, you will have to develop and then maintain a new one. But if you think about interoperability, usually it is easier to use a DSL as it would be more efficient. So the next question would be for you, profiles or DSL? If you want to adapt some concept from UML, just use the profiles. But if you want to hide some parts of the UML standard, profiles are not the good choice, because profiles must be used to complete the standards, not to change completely the meaning of concepts. OK, consequently, we are all working on the same referential, but how to keep the consistency? There are many different and complementary solutions for this. The first one would be to use a model repository that will ensure the consistency. Or you can use also continuous integration with consistency verification in order to link all the different components. Okay, so as a consequence of having one common referential, we have to think about how to work with a large amount of data. We need to be sure to use the good tools and search for dedicated and optimized tools. You have to pay attention to split the information in order to work on smaller, consistent pieces. To sum up, building a specific workbench is possible thanks to the Eclipse constellation, but in my opinion, it is missing an integration between tools and process. For the future, it would be interesting to integrate some projects used to describe the processes, such as EPF, with projects such as mailing context to link the appropriate tools to the different process steps. Okay, thanks for your attention. It's time for questions, so if you have any questions, do not hesitate. No? Okay, no questions. You can, okay, one question.
I just wondering, so, I mean, there's a lot of tools.
Yeah.
Presented here. Can you give an idea of the effort it takes?
To prepare this for integration, yes. All the tools were already existing. So for me, it was, I think, I spent 1 week for integrating all the tools.
Okay, using Obeo tooling?
Using the Obeo tooling and the EMF tooling, okay. And the EMF, CDO, and whole. But the tools are already existing. The only tool that does not exist was the link between the Rekiff standard and the SysML designer. And I developed this, and it was, I think, 1 day. So it's really, really easy to do. Okay. Other questions? No? Okay.